in sampling algorithms. There we saw that okay, we have like say Langevin Monte Carlo or some such algorithm for or stochastic gradient Langevin algorithm. We want to make its discretization better, or we want to have a tractable way to evaluate the drift function and so on with stochastic approximation. And I told you how we might want to approach the analysis. Okay, so the first method was that okay, there is a noise induced by your stochastic approximation, and there's a very large noise which is the Gaussian, and the sum of them looks approximately Gaussian, so you cannot distinguish your approximation from the real thing. So if you can't distinguish them, they must be producing the same result. So it's actually accurate. So today we will switch gears and go to one of my more recent works, which is the second kind of stochastic approximation which I thought about, which is actually closer to what we think of in optimization. So this is actually has a gradient descent structure, and this is actually an optimization algorithm in the space of probability distributions. Okay, so this is a kind of different way of showing convergence of stochastic approximations. Okay. So in this talk, I'll consider the concept of mean field optimization. So what is mean field optimization? We have a functional f which maps the space of all probability distributions with finite second moments over Rd to a number. Okay. Why is this not working? Okay, so this is the space of probability measures with finite second moments, and this is the functionals. Yeah. Okay. So right. So the task is to find pi star is equal to argmax argin of this functional as p belongs to in this space. Okay. I'll make the assumptions. So this is the overarching theme. Okay. So example 0 is sampling. We saw this yesterday, and actually sampling can be seen as this kind of an optimization problem where the functional is KL divergence from p to pi star, and pi star is this thing. So everything we saw yesterday is a case of this thing, example 0. Okay, but why do I call it example 0? There is no mean field problems here. You can just actually implement discretizations of this, but it is still fits in a trivial way to the theory I'm about to propose. Okay. Yeah. So okay. So let's see some structure here. So we have if we write down the KL divergence of this, the first term is the energy. We will think of this as energy based on physics. So integral f of x dp of x is the expected energy under this probability distribution, and this is the entropy. So yesterday I was talking about how if you run Langevin Monte Carlo, it's kind of tries to go towards the global minimizer, but then this entropy makes sure that it goes away. The Brownian motion makes sure that it goes away from it, so it becomes a sampling algorithm. It doesn't settle anywhere. Okay. So and this is the negative entropy. Okay. So we can solve this. We know how to solve this approximately. We have error bounds for it. We just use sampling algorithms. Okay. So okay. So let's go to the next non-trivial matter here, that is pairwise interaction energy. So here is where things start getting more interesting and harder. Okay, so I showed you how I wrote it as energy plus negentropy before. Now I'll show it as energy plus pairwise interaction energy, pairwise self interaction plus negative entropy. Okay, so this actually is beyond usual sampling algorithms. I'll explain to you why that is beyond usual sampling algorithms and why it usually requires a particle approximation to the algorithm, and how we can make the particle approximation actually make sense with stochastic approximation. Yeah.
Apart from physics, does this structure come up in like machine learning or?
Yeah, that's the next thing. Okay, so the more machine learning-y thing is the next slide, which is mean field neural network. Okay, so this can be seen as a optimization in the space of probability distribution. So what are we seeing here? Let's consider x as a data point here and theta as my parameter. So sigma of theta comma x is activation function with weight theta and data point x, right? You can think of it as a ReLU, and a two-layer neural network can be seen as an integral of these activations with respect to this distribution theta. So this is in the mean field regime. You take an average of certain weights and then you assume that you take the thing to infinity and then it becomes an integration. Even with finite, it's a finite measure basically. So it captures a lot of neural network theory. Okay, and then this is like an L2 error on this and the expectation overall data point. So you want to predict y with x with this mean field neural network. Okay, and then this is a regularizer in this in the weight space, that is you don't want the weights to become too large, and this is a regularizer in the space of probability distributions, is the negative entropy. So you don't want it to become a Dirac delta, for example. You want it to have a density, smooth density for it. Okay, so these are the regularizers, and first thing ensures that the neural network must fit data.
What's the entropy term?
Huh?
The neural network.
It's okay. It will prevent your weights from becoming Dirac deltas, for example. Yeah. Or having atoms. It will give it a smooth density. Okay, so let's think about gradient descent based algorithms, right? So we want to optimize that, and what is used in currently in Euclidean spaces. So it is highly successful in machine learning for optimization in Euclidean spaces. In fact, it's too successful and we don't know why, but that is a different question altogether. But let's assume that it is successful and we want to mimic this success everywhere else. So we have a function f from Rd to R, and we have something like a gradient descent. We have xt plus 1 is equal to xt minus alpha gradient f hat of xt, where this is called the stochastic gradient. We don't usually have the exact gradient because it's too expensive to compute. So we have something like a stochastic approximate, which is expectation grad f hat of xt given xt is equal to a grad f of xt, and we descend along this direction. And then how do we show its convergence? It's usually through a Taylor series expansion. You assume the Hessian is bounded, then you have like, okay, well, how far is the next iterate from x star, which is the actual minimizer? It is less than or equal to the previous difference minus mod gradient square plus O of alpha square. O of alpha square is the second order Taylor series, and you take expectation on both sides and you obtain such an expression, and it converges to global optimizer under the Polyak-Loyasev condition. So what does it mean? It means that if the gradient gradient actually dominates the difference, right? So it means that if you are far away from the optimal, you actually see a large gradient. So you actually end up going to the solution x star. Okay. So this is one of the hundreds of different conditions which ensure that you actually converge to the optimum in stochastic optimization. It is an assumption on F. PL condition.
Just that.
And Hessian bounded. No, it's not convexity. But convex functions satisfy this, right? So it's, yeah, correct. Okay, so this is so successful. So we asked the natural question: can we come up with analogs of stochastic gradient descent for mean field optimization? And this will be the topic of today's discussion. Okay, so so for that we need a concept of gradient. So we'll think of Wasserstein gradients. Okay, so we have f of p, which is scale from p to pi star, and pi star is this Gibbs distribution. Okay, and then we have this Langevin dynamics, which we saw yesterday too. This is dxt is equal to minus gradient f of xt dt. This is a gradient flow in the Euclidean gradient flow for f of x, and a Brownian motion dbt. Okay, this satisfies something called the Fokker-Planck equation. Okay, so now if x naught has a certain distribution, that is p naught, and if I go take xt through this Langevin dynamics, what happens to the density of xt? Right, it satisfies something called the Fokker-Planck equation. This is very classical. Actually, it's Fokker-Planck-Kolmogorov, as some people pointed out, because Kolmogorov also worked on it in the mathematics literature. So this shows how does the density change at x. It changes based on this divergence. It follows this velocity field which is minus gradient f of x. So this shows that okay, things flowing in a velocity field cannot lose or gain mass, and this is because of the Brownian motion diffusion. Okay, it's second order because diffusion has a local scale of root t. So second order fluctuations get picked up, Hessians get picked up because of Brownian motion. If you look at Ito's formula, for instance. Okay, so this is the Fokker-Planck equation. Okay, so the one of the foundational results in mathematics and PDE theory and optimal transport theory is that Fokker-Planck equation is actually a gradient flow of the KL divergence under the geometry of two Wasserstein distance. This was one of the towering results from the 90s, which showed that okay, we know that if I block out, scratch out this Brownian motion, it's a gradient flow, but in Euclidean space. But if I add this Brownian motion, it is still a gradient flow in a different geometry. It is an infinite dimensional geometry of the space of probability distributions, but it's still a gradient flow. So this tells us that it is optimizing something, and it is actually optimizing the KL divergence. We are running gradient descent on the KL divergence, right? And we want to push this further into the realm of mean field optimization. Okay, so let's actually stock up and do some comparisons. So you have a gradient flow of this sort, and here you have the flow is a Fokker-Planck equation, and here the convergence criterion is something called the PL condition, and here the equivalent thing is something called logarithmic Sobolev inequalities. So what are we seeing here is that okay, the gradient is greater than or equal to function value difference. Here this Fisher divergence is something like gradient squared. I'll explain to you why that is, but trust me on this, Fisher divergence is like gradient squared, and its first order optimality should imply zeroth order optimality in some sense. That's what. Sorry? A mu here is any point. This is called a, okay, this class of inequalities is called a functional inequality. So this holds over P2 of RD. So here this holds for all x. X star is your optimal, and this inequality where first order gradient squared is greater than or equal to function value difference, this doesn't hold for any x, it doesn't hold for some particular x, it holds for every x. So this is called a functional inequality. So what does it mean? It holds for every probability distribution mu. So you give me anything where this holds, then I will show that Fisher divergence between mu to pi star is greater than KL divergence between mu to pi star. This also holds when KL divergence is infinity, because then it ensures that Fisher divergence is also infinity. So yeah, this class of inequalities is called Log-Sobolev inequalities. Yeah. I don't know if it's in the talk, but I can do it on the board real quick. Fisher divergence is basically integral this is the quantity. Okay. Yeah.
There are not would depend fully on pi star.
Correct.
So what do you mean pi star?
So for example, lock concave works. Okay, lock concavity, strong lock concavity works. So that is F here should be strongly convex, right? And that is a classical result which shows that LSI holds in that case. And CLSI is 1 over the strong lock concavity constant. With a bounded perturbation, the Radon-Nikodym derivative will follow a Log-Sobolev inequality, but it will not be lock concave in this setting, right? So that is one of the reasons people study this, because it can model some amount of bounded ruggedness in the landscape of the Gibbs distribution. Okay, so that it's called the Holly-Strook criterion, if you want to look it up. Yeah.
You wanted that second squared mean square.
Well, that's one of the reasons. Of course, all these quantities start making sense only then. Even if pi star is Gaussian, for KL to be finite, you need a second moment. Okay, so but more importantly, when I go to Wasserstein 2 distance, right? You cannot even describe that space with distance without second moments. Yeah. So if you work with Wasserstein 1 space, then you can get away with first moments, but then you don't have the geometry which comes with Wasserstein 2 distance. Okay, so let's actually go through the concept of Wasserstein distance and Wasserstein gradients. Okay, so I said that okay, there is this nice distance in the space of probability distributions, and I'll describe a geometry on this, and I'll do this. So for that we need a distance. Okay, so what is W2 of mu comma nu? It is square root of the square distance infimum over all couplings between mu comma nu of the square distance. So what does it mean? So coupling between mu comma nu is a joint distribution. Okay, so you get two random variables out of this, x and y. X is distributed as mu and y is distributed as nu. Okay, so and then I'll consider the distance between x minus y squared under this coupling. One trivial coupling is independence, right? X and y are independent, x is from mu and y is from nu, and then I'll do it. We don't expect that this will achieve infimum, right? But there might be tighter things, how to move one distribution to the other in a more optimal manner, and the best such movement is gives you the optimal coupling, and we know that it exists under very minimal assumptions, and on RD we know that there is an optimal coupling. Okay, so I'll make take an infimum over this, and I'll describe the Wasserstein distance as this least amount of cost I pay to move one distribution to the other distribution. Okay, so we know that P2 of RD is a separable metric space under Wasserstein 2 distance. It shows that it is in fact a distance, and the topology induced by it is not actually too bad. So you can do probability theory on this because it is separable, and so on. I am happy to describe more about what this means if you want more description. Okay, and it's actually quite reasonably easy to see why it is a separable metric space under 2 Wasserstein distance. But I'll give you a more important structural theorem here, which actually blew my mind when I first saw it, but it is actually a standard now in PDE theory. Is a characterization of a continuous curve in this geometry, and that tells us a lot about what all dynamics can we expect on this space. Okay. Okay, so let's consider Pt from 0 comma t. It's a time dependent probability distribution. It's a trajectory in the space of probability distributions depending on one variable which varies from 0 to t, and this is an absolutely continuous curve. If you have not heard of what an absolute continuous curve is, it's slightly more stringent than uniform continuity, but it is kind of like uniform continuity. Okay, so I won't go into the gory details of what that means, but suppose it is an absolute continuous curve. Okay, under the Wasserstein 2 distance. Okay, then there exists a velocity field Vt. Okay, what is a velocity field? Velocity field is a map which maps an x to a velocity vector in Rd. It is a map from Rd to Rd, and it varies across time. Okay, so now there is a velocity field like this such that the continuity equation is satisfied in the weak distributional sense. So what I'm saying is that okay, this continuity equation holds, and this is weak in the sense that this okay, I don't know if people are familiar with weak solutions to a PDE. There are strong solutions and there are weak solutions. If P has a differentiable density, smooth density, and so on, this holds pointwise. We think of these as derivatives, and this holds. But what if it's a Dirac delta or something? You can still define solutions to PDEs when they are generalized functions, and it holds in a suitable weak sense. There is a notion of that, but we can for now assume that it is actually a smooth density and goes through this. So to give you more details as to why this continuity equation is important, there is a classical theory called for ODE to this PDE. There is a connection. Okay, so we suppose we have an ODE of this form, dxt by dt is equal to Vt of xt. So this is a classic ODE. Most ODEs can be written like this, and so let's say x naught is random p naught, and xt, then I solve this and xt is distributed as pt, right? Then pt satisfies this continuity equation. Okay, and there is also theorems which say that if vt and pt are sufficiently well behaved, then the solution can be obtained exactly through this equation, right? They have to, it's a two-way street in some sense. Okay, In fact, there is a more tangent space structure to this. So when you think of manifolds and geometry, you think of tangent spaces. Okay, where how all could this velocity move? So in some sense, this is how things move in the space of probability distributions. Moves as continuity equation, and just like particles move along, certain directions in Euclidean space. And we also have a notion of the tangent space of this manifold, and the tangent space is this funky space. Okay, so what is this? You take a function phi in CC, infinitely differentiable compactly supported function, and you take the gradient of this function, and you take this L2 closure of the space, and this is all the kind of velocity fields which are possible here. What this ensures is that if you pick one velocity field, there exists a velocity field like this which will satisfy the continuity equation. That's all we are saying. Okay, so just by assuming this geometry, we got that, okay, most of these nice continuous curves satisfy this equation. Okay, this is a deep structural result. Okay, so now we know how things move. Okay, so in the Euclidean space, we had this ODE. This is how things move in the Euclidean space, and then I said that, okay, if I pick Vt of xt is equal to negative gradient f of xt. Right, I made this specific choice. I told you there's a potential function. I'll take this as the gradient, and then it became gradient descent or gradient flow. Right. So, and how do we do gradient flow here? So we took a tangent space, and I'll find an element in the tangent space which minimizes my functional, and that is what I'm going to do. So we have a functional f from P2 of Rd to R. I told you this before, and then I'll have the first L2 variation of this functional. Okay, I don't know if everyone is familiar with what an L2 variation is. It's from calculus of variations. No? Okay. Okay, well, here's a definition of what an L2 variation is. We'll think of probability distribution as a density. Okay, density is a function, and then what I'll do is I'll go have P and add a function epsilon to this P. Okay, and I'll consider what is f of P plus epsilon minus f of P. This is exactly calculus of variations, and if there exists a functional delta f of P comma x such that this can be written as f of P plus epsilon minus f of P is equal to this integral plus O of epsilon squared, right. So then we say that this delta of f p comma f x is a L2 variation of my function. So if I perturb my density, how does my function value change? So why is this in L2? Because fp plus epsilon need not be a probability distribution at all. It is any arbitrary perturbation. But this will be actually connected to Wasserstein gradients shortly. Okay. And then there's a lot of theory developed in the late 90s and early 2000s which said that, okay, what is the right notion of gradient here? The Wasserstein gradient, this in the space of probability distributions, it's you take this L2 variation which takes input is probability distribution and a vector, and it gives you a number, right? But then what is the Wasserstein gradient? You take gradient with respect to x of this. Okay. So then we show that this is the right notion of the gradient in the Wasserstein space, and the gradient flow in this case is where you take the velocity field Vt to be this gradient f of Pt comma x. I think it should be a negative, but it's okay. Okay, it's a typo. Okay, and this is how I define gradients in this space. Okay, so this is how what we have. So now let's look at the prototypical example, non-trivial example in this case. So what is the Wasserstein gradient for the interaction energy? So let's recall what this interaction energy is. So we have this energy that is f of x dp of x, and then there's a self interaction, there's a w of x minus y. So what I'll do is I have, let's think of it as a field, I'll draw two elements independently from P, and then I'll compute w of x minus y. So we think of it as a repulsion in the sense that if they get too close, the energy becomes large. So it repels two particles from the same distribution. Okay. So this is repulsion, and then there is this entropy term which actually adds entropy. It prevents things from becoming Dirac deltas. Okay. It makes sure it has a smooth density. The gradient in this case is the Wasserstein gradient in this case is grad of x plus grad w convolved with p. Okay, this is I mean we can actually work it out. It's a simple 5-minute calculation using the definitions. I'll skip it and hope that you will do this later. and then you have this sigma square over 2 gradient log p of x. Okay, so if I want to implement this, okay, so then this is actually it is in the path space. Like I said, Langevin dynamics, if this wasn't there, this Langevin dynamics corresponds to gradient flow of the KL divergence, right? So now if I want to implement this in the path space, I'll have to do something called the Mekin-Vlasov equations. Okay, this is not an Ito differential equation, it's a Mekin-Vlasov equation. What is different here is that I have dxt is equal to minus grad of xt dt plus sigma dbt. Sigma dbt corresponds to the gradient flow of grad of this negentropy. Okay, but what is additional is this grad w star convolution pt. Okay, so this drift term depends on the law of the iterate. It doesn't just depend on the iterate, but on the law of the iterate. So we don't know how to get this just by looking at xt. So we cannot run this easily on a computer. So that is the source of all our problems, and that is why we need stochastic approximation. Okay, so we know that optimizer to this under certain conditions is a solution to the following fixed point equation. You see, if it was just Langevin Gibbs sampling, there would be no this term, so it's not self-referential. Pi of x doesn't appear on both sides, right? But now this is actually an answer to a fixed point equation, and pi of x appears on both sides. Okay, so rest of the talk is like, okay, how do we algorithmically deal with this problematic term when we are simulating this on a computer? Okay, so the usual method is to use an n particle system for large n. I'll describe this solution. Okay, so what we do is that, okay, we take n particles, dxti is equal to, we run this Langevin chain, but however, when we have to take this average with respect to this probability distribution, we actually make it pt hat, which is the empirical distribution of all particles, right? So this is the usual particle methods in physics and everywhere used to simulate these systems. Okay, okay, so there are many questions here. So how do we know that this converges to the optimum, and can we demonstrate the rates of convergence and computational complexity? Okay, there is one possible method to show this. This is just one possibility. So we show that the n particle system converges to an optimum of some n particle objective function in nd dimensions. So it's an n particle dynamics, and then we show something like, okay, for large n, the n particle optimum is close to the mean field optimum pi of x. Okay, so there is some kind of a scaling law happening here. This is called propagation of chaos. This has been very classically studied by Schnitzman and Malrieux and so on, and then non-asymptotic convergence of this has generated a lot of interest in the recent years because of applications to both ML and to the probability theory. Like I showed you, there is a physics angle to this with interaction energy, and also mean field theory of neural networks. This is of interest to the ML community. See, this is okay, if I take all n particles, this is an Ito differential equation in nd dimensions, right? So that will converge to something, or hopefully it converges to something, or we can show that it converges to something.
I see. That was that second one, saying the optimum, whatever.
As n tends to infinity, what is the optimum, right? So what is the guarantee that what I converge to here will sample from the right thing? Okay, so what is the problem in this? Okay, so we need to show that, okay, if we want to show that it converges to some n particle objective function, we need to show some logarithmic Sobolev inequalities in nd dimensions for this very hard system. Like I showed, log Sobolev inequality shows that first order optimality implies zeroth order optimality. So this is very hard to show for anything for distributions in general, right? So Gaussian log Sobolev inequality is easy, and then you do perturbations of that. Concave, for log concave distributions, it's easy, and you do perturbations of that, and beyond that, it's actually very hard to show this. Okay, and the constants are desired to be independent of n. The log Sobolev constants show us how well conditioned the problem is, right? And we want it not to be large and not dependent on n, right? And that can be very hard. And this can get technically very, very involved. It uses transportation arguments from some distribution to Gaussian distribution, Lipschitz transport, and so on. And it gets very, very involved, and people write 50-page papers on this. Okay, and okay, and the problem with choosing this is that, okay, for large n, the n particle optimum is close to the mean field pi of x. right? So what does this mean? It means that choosing k out of n particles gives approximately IID samples from pi of x. This is called propagation of chaos, and this can require additional specialized techniques like uniform in n log Sobolev inequalities, which is another can of worms, which is very, very hard to deal with, and there are no techniques which can give you a clean answer to these questions. Okay. So our work said that okay, these are all very hard questions. We don't know how to solve them. Or at least I don't know how to solve them. So what I'll do is I'll give an algorithm which does not have to reason about this n particle systems at all. Okay, which will just consider the mean field system and it will automatically give IID samples from close to the mean field distribution. The first part I avoid the first part and I avoid the second part. I don't have to prove. Yeah.
For showing it the closeness to pi star.
Correct.
Here you are showing that just for.
So think of it in abstract. Okay, so there's a pi n star here, which is the joint distribution.
First part.
What do you mean?
The field optimal pi x is only that the second part. So
where is pi? Here.
Yeah.
Correct. So, but this will converge to something, right?
Why? For that.
How will you show it converges?
I mean, it might converge, but it may not converge to pi x.
Correct.
Yeah.
So that's the second part. It will converge to pi hat x. It will converge to pi hat n x. So this is an ND dimensional system.
Yeah, but we needed lots of it.
Okay, think of this abstractly for any system in k dimensions. If you have Sobolev inequality on this, it will converge to something, right? So now take k to be n times d. So you consider this new system. If this new system converges to its optimal, okay, once it converges, you get some samples and show that as n is large, that those samples are approximate this pi of x, right? So first you need to show that this converges, and once this converges, you need to show that that is close to this, whatever it converges to. This is like empirical risk minimization and then showing that its optimum is close to the population risk minimization. Okay. Okay, so let's think about stochastic gradient descent now. So as I said, okay, this is about stochastic gradient descent. So what we saw was like empirical risk minimization, but I'll show population risk minimization with a new algorithm. Okay, so we consider the Wasserstein gradient here. So I'll ask the question, can we get an unbiased estimate of the gradient given x and p? Okay. So suppose x and y are IID from p, then we can consider g hat of x comma y, which is minus grad f of x minus grad w of x minus y plus sigma square grad p log p of x. This will become a Brownian motion, so it doesn't matter, but let's consider these two terms. So then their IID from p, then we have this is an unbiased estimate for the Wasserstein gradient which is given here, because if we just integrate out y, then we get grad w convolved with p. So I propose this following thing, which is called the virtual particle stochastic approximation. Okay, so I have these virtual particles and there are real particles. Virtual particles are required by the algorithm and the real particles are part of the output. Okay, so first there is a stochastic approximation, it requires a y, which is IID with these things. So I'll take g hat function with, I kill the virtual particle to estimate this function, and then I'll go one step using this function. Okay, and I'll evolve all the virtual particles and all the real particles. Okay, next I'll kill the next virtual particle, get stochastic gradient at time 2, and then I'll send everything to time 2 and so on. And so I'll at each time step I keep on killing a virtual particle to estimate the gradient. Okay, at the end at time 5, which I say that okay, I'll end my algorithm at time 5, I'll have only the real particles as part of the output. Okay, so this is a virtual particle stochastic approximation. We can see this algorithmically here. So we have xt, which is the result, and we have initialization x0 to xn, which is the real particles, y0 to yt, which are the virtual particles. They're all IID, and maybe there is some extraneous noise which I won't go into. And I'll evolve all of them by killing the kth virtual particle at time k, right? So and then I'll output these xt1 to xtn. Okay, so again, yesterday I showed you needle in a haystack type argument, but this is actually straight up Taylor series. How do you show the convergence? It's just Taylor series in the space of probability distributions. Okay, So what I actually show is that, okay, if you consider under this trajectory, you make a continuous approximation of the discrete trajectory, and then I have df by pt given ft by dt is equal to minus Wasserstein gradient squared plus discretization error plus stochastic approximation error. What is this script ft? Okay, there's a overload here. This f is a functional and this f is the sigma algebra of the first t virtual particles. But okay, let's not mind the overload here. Okay, this pt is the conditional distribution of, and given the first t virtual particles, and this is the function value of pt given conditioned on the first t virtual particles. Then you have this gradient descent term. This is the Wasserstein gradient squared in some the L2 sense, and there's a discretization error because we cannot run in continuous time, and there's a stochastic approximation error because we are using stochastic gradients instead of full gradients. Yeah. Because it's an unbiased estimator, like I said, it's you get IID particles now. Conditioned on FT, the virtual particles are IID. I'll show you. So this is gradient flow. This is this. Okay. So okay, here is the explanation. So we know the discretization error is of the order eta to the 3/2, which is eta is the step size, and stochastic approximation error is zero mean because of our algorithm, because it's an unbiased estimator. But if you use particle methods, it gives you a biased estimator of the gradient because all the particles are dependent on each other, right? So this won't be zero. It's very hard to handle this term in that case. Okay, and then the Lox-Sobolev inequality is actually show that, okay, this Wasserstein gradient squared is dominates the zeroth order error, and that's how you get exponential convergence, kind of. And then you apply Gromov lemma and it implies convergence. Of course, this also requires things like regularity and weak interaction assumptions, which are standard in literature. Okay. Okay, so here is the theorem. Okay, pi satisfies Lox-Sobolev inequality with constant CLSI. Grad f is L Lipschitz, grad w is LW Lipschitz, and LW is small enough. So this is a standard assumption, meaning that the interaction is not too strong, repulsion is not too strong. So now if I run the algorithm for this much time, then the real particles which form the output of our algorithm are IID from the random probability distribution mu t given ft, where capital Ft, script Ft is the sigma algebra of the first t virtual particles, and you have the IIDness. Like I said, you don't have to show IIDness, you already have IIDness, okay, such that KL from mu t given Ft to pi is less than or equal to epsilon. Okay, so this is my algorithmic guarantee. Okay, so one of the salient feature here is that this only depends on the LSI constant of pi of x. Okay, and the analysis of usual particle methods have a dependence on CLSI(n), that is the n particle Lox-Sobolev constant, which we have no idea how to bound. Okay, and bounding this requires additional assumption and or have exponential dependence on various problem parameters, additional exponential dependence on the problem parameters, which we usually don't desire. Okay, and we can actually obtain similar convergence results for the case of mean field neural networks, and I can refer you to my paper here. And yeah, I can answer any questions you might have. Yeah. Right.
What does application describe? What does being a particle?
Okay, so that's a good question. So okay, so in the usual particle methods, what happens is that, okay, you take all the particles, you have some estimate for this and apply it on all the particles. So what happens then? Everything becomes independent, right? So now if I go back to the stochastic gradient descent, you have this g hat term. Okay, so when is this an unbiased estimator for this grad f? So when x and y are IID. So, but if you keep on reusing the particles again and again, they are not conditionally IID. So you don't get conditionally unbiased gradients. So once you end up with biased gradients, you have no idea what the particles are doing. Right. So, so you hope that, okay, if n is so large, it's so representative that it is almost unbiased. But then how large should n be for that to happen? It's actually a very hard question to answer. So as many time steps as we have, right? We add t time steps. But then you can store the trajectory of this and generate as many real particles as you want, right? So like I said, if you go to the next slide, okay, what all do we need to run this algorithm more and more times? We need this sequence of g hats, right? If I just store these virtual particle states at time t, right, and give you a trajectory, I can generate as many real particles as possible by just running a flow along this. So I call that a witness path, right? If I can just store it and generate, make n as large as I want.
So for the neural network case, so first of all, I see this as a method to sample from
the optimal of the mean field, yes.
Right. So for the neural network, it's what exactly are we sampling for the?
It's the weights of the neural network. Let me.
And why is that?
It's an example, but yeah, it can solve this mean field. It's just an example derived from this. So I think we can think of this as, okay, maybe this is useful in if you want to do federated or learning or something where you have things living in different places, weights living in different places, and you have minimal virtual particle communication, and then you want to optimize it. Okay, but why do you want to do this? The thetas are the weights of the neural networks, which is what you want to learn by optimizing this objective.
I was thinking like, but the Bayesian inference can be something. For example,
Bayesian inference, if it involves mean fieldness, yes, but no, but in Bayesian inference, you already have this thing, right? This is how Bayesian inference works, right? This is the posterior distribution for which you have some kind of energy function. You can just run Langevin dynamics on this, right? So, yeah.
So once we figured out the action there in this particular case, we have this Ws minus y. And if I understood correctly, which I'm making the same, you're using the fact that the integration of a y essentially turns this into a convolution of the problem.
Correct. Yeah.
But there a more general sort of unbiased property that solves a more general task of
correct. So there is in the paper actually gives a more abstract theorem here. So you assume the existence of an unbiased estimator and so on and bounded thing. I just went through this talk but without going through the abstraction.
There a good example besides the interaction. Good examples of the more abstract theories.
So mean field neural network it also applies to the mean field neural network case. For example, if you have wherever you can have, so this L2 losses actually usually have this unbiased kind of thing. Yeah.
Why we get
okay. So one thing is that first regularizer, you don't want the weights to become too large. Second is that when you're running stochastic gradient descent, right? So the noise because of your batches, because you're using mini batches instead of your entire data set, looks like it can either look like a ballistic limit, which is an ODE, or it can look like a stochastic differential equation with some right Brownian motion term. So there are some theories which suggest that it actually looks like a converges to a stochastic differential equation limit. Okay, because of that it doesn't get stuck in local minima and it can come out of that. So how do you explicitly model that? If you want to do that, you kind of add this integral p theta and it becomes a Brownian motion so that you can study the stochastic differential equation limits.
all right, one person is standing.
Yeah.